Hello everyone, and welcome to today's presentation. I'm excited to introduce our topic, the activated sludge process. On this first slide, you'll see the title and a brief overview. Over the course of this presentation, we'll explore how activated sludge works as a secondary treatment method, focusing on its role in removing organic solids and suspended particles. We'll also look into the biology behind the process and how microorganisms are cultivated in aeration tanks. So, let's dive into understanding this essential process in wastewater treatment. In this slide, we're looking at the treatment process flow, which is essential to understanding how wastewater is cleaned before it's released back into the environment. When wastewater first enters an activated sludge treatment plant, the initial step is preliminary treatment. This stage is all about removing the large, heavy solids like grit, which includes things like inorganic debris, rocks, and sand, as well as other debris such as rags and boards that might be present in the water. Think of it as a first filter to catch the big stuff. Next, we have primary clarification. This step is sometimes optional but very effective. It helps remove the floatable and settleable organic materials, things like oils, grease, and other materials that can float or settle out easily. If primary clarifiers are used, they significantly reduce the load on the subsequent biological treatment stages. After these initial steps, the water moves into the aeration basin. Here, microbes play a crucial role. They consume the remaining organic solids using dissolved oxygen. This biological process is what makes activated sludge treatment so effective at breaking down pollutants. Finally, the secondary clarifier allows gravity to do its work, settling out the microbes and other solids that have been used up or transformed during aeration. The clarified water at this stage is much cleaner, ready for any additional treatment or discharge. Overall, these steps form a coordinated flow, ensuring that from the moment wastewater enters the plant, it's systematically cleaned through physical, chemical, and biological processes, all working together to protect our environment. Let's talk about some key operator controls that are essential for the successful operation of an activated sludge process. First, a skilled operator needs to be aware of and constantly monitor various process control factors that influence treatment performance. This ensures the microorganisms stay healthy and effective. One of the most important aspects is controllable influent feeding. It's crucial to manage how wastewater is fed into the system so that the load is evenly distributed across all aeration basins. Proper flow splitter boxes are designed for this purpose, and regular checks are necessary to make sure the flow remains balanced. Next, we have proper dissolved oxygen levels. For most activated sludge processes, maintaining a minimum of 1 milligram per liter of dissolved oxygen in the aeration tank is vital. Keeping oxygen levels above this threshold helps create an environment where microorganisms can thrive and do their job efficiently. Another control point is the RAS pumping rate. The rate at which return-activated sludge is pumped back influences how long solids stay in the secondary clarifier. Monitoring and controlling both the sludge blanket depth and the solids concentration in the RAS are key to maintaining proper solids retention and overall process stability. Finally, the concentration of mixed liquor is something we constantly adjust. The goal is to maintain the right amount of microorganisms relative to the food supply, which is the organic matter in the wastewater. This often means removing excess organisms through wasting, ensuring the microbial population remains balanced for optimal treatment. All these controls are interconnected and vital for keeping the process running smoothly and efficiently. Maintaining the right dissolved oxygen levels is crucial in our activated sludge process. Microorganisms need oxygen to oxidize wastes, which they use to generate energy for growth. If oxygen levels are too low, it can slow down the activity of these aerobic organisms or even kill them off entirely. This also affects facultative organisms, making them less efficient, and can lead to the production of unpleasant, foul-smelling byproducts from anaerobic decomposition. As the microbial population in the aeration tank grows, so does the demand for oxygen. Higher concentrations of BOD in the influent or increased influent flow will boost microbial activity and, consequently, oxygen requirements. That's why it's vital to always maintain sufficient oxygen levels to ensure complete waste stabilization. Now, if the dissolved oxygen drops too low for an extended period, we risk encouraging undesirable organisms, like filamentous bacteria, which can disrupt the process. On the other hand, if oxygen levels become too high, especially during colder weather, we might see problems like flock particles floating to the surface in the secondary clarifiers. This brings us to the importance of critical dissolved oxygen monitoring. It's essential that the system operator regularly checks the DO levels using a DO meter. Monitoring oxygen is one of our key control points. It helps us keep the process running smoothly and prevent issues that could compromise treatment efficiency. Now let's talk about the food-to-mass ratio, or F-M ratio, which is a key concept in understanding how the activated sludge process works. Essentially, this ratio describes the balance between the amount of available food, which is the organic material in the wastewater, and the mass of microorganisms present in the system. The main job of an operator is to maintain the right amount of microorganisms relative to the food supply. Since the food supply, or wastewater solids, generally stays fairly constant from day to day, the challenge is adjusting the microbial population accordingly. When we have a high F-M ratio, that means there is too much food for the number of organisms present. This typically results in a few telltale signs. The effluent becomes cloudy, large flock particles are visible, the mixed liquor appears light brown, and you might see frothy foam on the surface. This situation usually indicates the system is overloaded or in its startup phase. On the other hand, an ideal F-M ratio reflects the perfect balance. Here, the effluent is clear, the mixed liquor has a nice chocolate brown color, the foam is crisp white, and the flock particles are strong and well-formed. This balance allows the system to produce excellent settling sludge and results in low levels of BOD and TSS in the effluent. Finally, a low F-M ratio occurs when there is not enough food for the microorganisms, meaning too many organisms are present. This leads to some undesirable signs: thick, dark foam, a dark brown or reddish mixed liquor, rising sludge, and pin flock in the effluent. In this case, the system needs more waste removal, or wasting, to restore the balance. Understanding and managing the F-M ratio is crucial because it directly impacts the treatment efficiency and the overall health of the wastewater treatment process. Now, let's talk about how we actually calculate the F-M ratio in an activated sludge wastewater treatment plant. To do this, we need two key pieces of information. First, how much food is entering the aeration basin each day, and second, how many pounds of microorganisms are available in the basin to consume that food. The food amount is determined by calculating the BOD loading, which is expressed in pounds per day of influent entering the basin. Think of BOD as the measure of the organic matter that microorganisms will break down. Next, to find out how many microorganisms are present, we look at the mass of mixed liquor volatile suspended solids, or MLVSS, in the basin. This measurement gives us an estimate of the microbe's biomass because it's based on the volatile solids, which are assumed to be entirely made up of living microorganisms. It's important to note that when we use volatile suspended solids in this calculation, we're assuming all of those volatile solids are living microbes. The non-volatile solids, on the other hand, are inert and don't play a role in metabolizing waste. To make this clearer, let's consider an example. Imagine an extended aeration plant operating at an ideal F-M ratio of 0.08. This example helps us see how these calculations come together in real-world scenarios. Let's take a closer look at the different types of activated sludge processes. First, the conventional activated sludge is the most common method used today. It typically involves a detention time of about 4 to 8 hours, with mixed liquor suspended solids, or MLSS, ranging from 1,000 to 4,000 milligrams per liter. The system's solids retention time, or SRT, usually falls between 3.5 and 10 days. The F-M ratio, which is the food to microorganism ratio, is generally between 0.25 and 0.5 to 1. RAS pumping can range from 15 to 75% of the influent flow. This process usually includes primary clarification before the aeration basin, producing high-quality effluent and handling small shock loads effectively. Next, we have extended aeration systems. These operate with longer detention times, about 12 to 24 hours, and higher MLSS levels, roughly 2,000 to 5,000 milligrams per liter. Their SRT exceeds 10 days, making them more stable, especially in smaller or packaged treatment plants. The F/M ratio here is lower, around 0.05 to 0.15 to 1, reflecting lighter loading. RAS pumping can be quite high, up to 150% of influent flow. While very stable, they may discharge slightly higher suspended solids compared to conventional systems. Finally, there's contact stabilization. This process involves a short contact tank detention, about 0.3 to 3 hours, followed by a stabilization tank for 4 to 8 hours. The MLSS in the contact tank ranges from 1,000 to 3,000 milligrams per liter, and the overall SRT is less than 3.5 days. The F/M ratio here is higher, from 0.5 to over 1, indicating a heavier loading. RAS pumping varies from 25 to 100% of influent flow. This mode aims to rapidly capture and separate solids, making it ideal where quick solids removal is necessary, especially when other modes might struggle with short SRTs and detention times. Understanding these variations helps us tailor treatment processes to specific plant needs and wastewater characteristics, ensuring we optimize performance and effluent quality. Let's take a closer look at aeration systems overview. Aeration plays a crucial role in wastewater treatment by providing dissolved oxygen and ensuring proper mixing of the mixed liquor and wastewater in the aeration tank. Now, there are two main methods used to disperse oxygen from the air to the microorganisms: surface aeration and diffused aeration. Both are mechanical processes, but the key difference lies in where the driving unit is located, either directly in the basin or at a remote location. Starting with surface aerators, these typically use a motor-driven impeller or a brush rotor. These devices splash the mixed liquor into the atmosphere above the tank, which allows oxygen to transfer into the water as the liquor passes through the air. These aerators can either float on the surface or be mounted on supports within or above the basin. They tend to have relatively lower installation and maintenance costs, making them a versatile choice. However, in terms of efficiency, they generally transfer about 2 to 3 pounds of oxygen per hour per horsepower, which is good but not as high as some other methods. Moving on to diffused aeration systems, these are actually the most common type in activated sludge processes. The key component here is the diffuser, which breaks up the airstream from blowers into tiny bubbles within the mixed liquor. The smaller the bubbles, the better the oxygen transfer because of the increased surface area of each bubble as it rises through the water. Usually, diffusers are placed near the bottom of the aeration tank, attached to air headers, to maximize contact time between the bubbles and the mixed liquor. This setup helps improve oxygen transfer efficiency significantly. So, to connect this to the broader picture, understanding these two methods is key to optimizing aeration in wastewater treatment. Each has its advantages, and choosing the right system depends on factors like cost, efficiency, and specific process requirements. Let's talk about aeration blowers, which are essential for providing the air needed in diffused aeration systems. These blowers are generally either positive displacement, also known as rotary blowers, or centrifugal, which are turbine blowers. They deliver air through a system of pipes or conduits to various parts of the plant. Starting with positive displacement blowers, they work by using a set of opposing lobes that mesh closely together. These lobes are driven by an electric motor. The key point here is that they provide a consistent amount of air per revolution, which makes them very reliable for maintaining steady airflow. They usually run at low RPMs and produce less than 20,000 CFM at about 5 to 10 psi. An important aspect is that changing the blower's speed can vary its output, offering some flexibility. Now, moving to turbine blowers, these have a motor connected to turbine blades on a steel shaft. The airflow is controlled either by a throttle butterfly valve on the intake side or by adjusting the RPM of the motor itself. These turbines operate at much higher speeds and can deliver between 20,000 to 150,000 CFM at pressures similar to the positive displacement blowers, around 5 to 15 psi. They tend to be more efficient for handling larger volumes of air. Finally, a quick maintenance tip. Experience shows that the lifespan of positive displacement blowers can be significantly extended if we use synthetic oil rather than petroleum-based oil. Synthetic oil resists viscosity breakdown better, especially under the high operating temperatures these blowers often run at, helping to keep them running smoothly longer. Understanding these differences helps us choose the right blower for each application, ensuring efficient and reliable aeration across the plant. Now, let's take a closer look at the different types of diffusers and their performance. First up are the fine bubble diffusers. These include plate, tube, and dome-type diffusers, all of which produce very small air bubbles. The key advantage here is their high oxygen transfer efficiency, typically ranging from 6 to 15%. However, a challenge with fine bubble diffusers is that they can be easily clogged. This can happen either from the inside, due to dirty air, or from the outside, because of biological growths. Keeping these clean is essential for maintaining their performance. Next, we have the medium bubble diffusers. These are often made from porous materials like nylon, Dacron socks, fiberglass, or saran-wrapped tubes. They strike a good balance. They provide decent oxygen transfer rates while being less prone to clogging than fine bubble diffusers. This makes them a practical choice when you want effective aeration without excessive maintenance. Finally, let's look at coarse bubble diffusers. Typically made of plastic, they come in a variety of shapes and sizes. Their oxygen transfer efficiency is lower, around 4 to 8%, but they are also more cost-effective. One of their main advantages is that they're relatively maintenance-free. That said, if the inlet works aren't effective at removing debris, rags can clog these diffusers, which is something to keep in mind. Overall, understanding these differences helps us select the right diffuser type for our specific needs, balancing efficiency, maintenance, and cost. Let's talk about safety considerations when working around aeration tanks and clarifiers. First and foremost, always follow safe procedures and exercise extreme caution. These are critical areas, and safety should never be compromised. Personal protective equipment is vital. Wear safety shoes with steel toes, shanks, and slip-resistant soles to protect your feet. When working around aeration tanks that lack guardrails, it's essential to wear a Coast Guard-approved life jacket. Keep in mind, because of the air bubbles in the tank, a person without flotation devices isn't buoyant enough to float or swim. Even with a life preserver, currents can pull you under, so always stay cautious. Facility maintenance also plays a key role in safety. Regularly scrub and wash away slippery algal growths on walkways. Keep the area free of spilled oil or grease, which can cause slips and falls. Make sure tools, equipment, and materials aren't left in places where they could pose hazards. Plus, ensure there is adequate lighting, especially for night work or emergencies. During winter, icy conditions might require spiked shoes, and sanding icy areas is essential to prevent slips. Now, let's discuss lockout and tagout procedures. Whenever maintenance or repairs are needed on the aerator, it must be shut down properly. The main power breaker should be opened, locked out with a padlock, and tagged with clear information, date, reason, and the person responsible. Keep the key in your pocket to prevent accidental re-energizing. Only qualified electricians should troubleshoot or repair electrical issues to ensure safety. Moving on to blower safety. Always wear appropriate hearing protection when working near an operating blower. The protectors should reduce noise exposure to a safe level, generally not exceeding 90 decibels over an 8-hour period. Before starting the blower, double-check that all inlet and discharge valves are open throughout the system. Remove any foreign matter to prevent damage or blockage. And before starting, make sure all personnel are clear of the blower to avoid injury. In summary, safety around these equipment and areas isn't just a set of rules. It's about protecting yourself and your team, ensuring smooth operations, and maintaining a safe environment for everyone involved. Let's talk about process control strategies in wastewater treatment. It's essential that all systems are operated based on a clear strategy to keep everything running smoothly. For activated sludge plants, operators need specific procedures to manage 4 key areas of the process. Over the past century, many strategies have been developed to help operators understand what's happening inside the system and to make the necessary adjustments to keep it balanced. First, we have visual observations. Using sight, sound, smell, and even touch can be incredibly valuable. For example, the color and odor of the mixed liquor can tell us a lot about the process. When everything is working well, the activated sludge should smell like healthy, wet soil. If something's off, these clues can help us identify issues early. Next, we look at MLSS and MLVSS concentrations. Operators often judge how much waste to remove based on the mixed liquor concentration in the aeration basin. Most systems operate within a range of 1,000 to 5,000 milligrams per liter. Keeping this concentration steady helps maintain the correct food-to-microorganism ratio, which is vital for effective treatment. Then there's the Sludge Volume Index, or SVI. This index shows us how well the sludge settles at a given MLSS level. It's especially useful for spotting filamentous bacteria outbreaks. A good SVI range is typically between 80 and 120. If it rises above 150, it's often a sign of a serious filamentous problem that needs attention. We also consider the mean cell residence time, or MCRT. This measures the average time bacterial cells stay in the system before being removed. It takes into account all the solids in the system, both those in the treatment process and those exiting each day. Understanding MCRT helps us control the growth and activity of microorganisms effectively. Finally, light microscope analysis offers a direct look at the microorganisms themselves. It allows us to assess the structure of flocks, the diversity and activity levels of the organisms, and detect any filamentous bacteria. This microscopic view provides invaluable insight into the health and stability of the biological process. All these strategies work together to give us a comprehensive picture of how the activated sludge process is performing, helping us make informed decisions to keep it running efficiently. Let's take a closer look at the settleometer test. This is a key method we use to simulate how activated sludge settles in a secondary clarifier. Essentially, we take a sample of mixed liquor, usually about 1 to 2 liters, from just before it enters the secondary clarifier. This sample is then placed into a special settleometer container, which looks like a large, clear, graduated beaker. It's marked in milliliters per liter and percent by volume, making it easy to observe and measure. The test involves monitoring the sludge's settling behavior over time. We observe and record the settling every 5 minutes for the first half hour, then again at 60 minutes and 120 minutes. But the most critical reading is at 30 minutes. If, at that point, the sludge has settled to around 300 milliliters per liter, or about 30%, and the supernatant is clear, that's considered ideal. It indicates that the sludge will settle quickly and form a compact layer in the secondary clarifier. Many operators graph these 5-minute readings over the first 30 minutes. This helps visualize the settling pattern, producing a characteristic curve. Such a curve provides valuable insight into the settling characteristics of the sludge, helping us make informed operational decisions. Now, interpreting the results is just as important. If you notice the sludge rising to the top of the settleometer within 120 minutes, it's a sign that the system is actively nitrifying, likely due to denitrification. This rising sludge is a good sign that biological processes are functioning properly, but it does mean we need to watch our return-activated sludge pumping rates carefully. Ensuring those rates are high enough prevents sludge from rising in the secondary clarifier, maintaining system stability. This test is a practical, visual way to assess sludge performance and helps us optimize our treatment process effectively. Let's take a closer look at how we calculate the Sludge Volume Index, or SVI. This is an important tool for analyzing the settling characteristics of sludge at a specific MLSS concentration. Essentially, the SVI helps us understand how well our sludge will settle, regardless of whether the MLSS is at 1500 mg/L or 3500 mg/L. To determine the SVI, we need to know both the sludge's settling behavior and its MLSS concentration. The key point here is that the SVI acts as an index. It's a way to quantify how effectively the sludge settles under given conditions. Now, what do these SVI values tell us? Values between 80 and 120 are considered within the good treatment range. When we see SVI in this range, it indicates that the system is operating under ideal conditions, with proper settling characteristics. If the SVI drops below 80, that's often a sign of older, fast-settling sludge. Sometimes, this means we need to waste solids to maintain proper operation. Interestingly, some systems, like sequencing batch reactors or SBRs, can operate consistently in this range without issues. On the other hand, when the SVI exceeds 150, that's a red flag, indicating a potential bulking problem, usually caused by filamentous bacteria. This is a serious issue because it can lead to the loss of solids from the system if not addressed promptly. Most importantly, the SVI is a valuable tool for early detection, especially for filamentous organism outbreaks. It allows operators to intervene before the system spirals out of control. Keep in mind, though, that these ranges are guidelines, not strict rules. Different systems have different secondary clarifiers, some shallow and poorly baffled, some deep and well baffled, and their responses to bulking conditions can vary. For example, a deep, well-baffled clarifier might handle SVI values above 150 without losing the sludge blanket, whereas a shallow one might struggle. So, understanding your specific system is crucial when interpreting these numbers. When we look at the mixed liquor in the aeration basin, it might appear to many as simply muddy water being stirred around in a big tank. But what's really fascinating is that this muddy appearance actually contains a vibrant community of living organisms. The light microscope allows us to see these tiny life forms, which are essential for the activated sludge process. It's one of the most powerful tools for assessing how well the system is functioning. Now let's talk about flock structure. When you examine the flock particles, look for ones that are large, solid, and light brown, with clear water separating them. That's a good sign. It indicates the sludge is healthy and will settle well. Conversely, if you see small, dense particles and the supernatant is filled with debris, that suggests the sludge isn't in good shape and might cause the water to be cloudy. Next, observe the other life forms present in the sample. You'll likely see a variety of higher life forms like amoebas, free-swimming ciliates, stalked ciliates, flagellates, rotifers, and even sludge worms. The types and abundance of these organisms can tell you a lot about how the system is operating, for example, whether it's balanced or in need of attention. Finally, take a close look at the spaces between the flock particles. Are there any long, hair-like structures protruding out? These are filamentous bacteria. When these bacteria become too numerous, they can interfere with flock formation, preventing particles from coming together properly. This often leads to bulking, which is a common issue in activated sludge systems. Recognizing these signs early helps us manage and maintain optimal treatment performance. Let's take a closer look at microorganisms and sludge quality. Every aspect of these higher life forms can tell us a lot about the health of the system. For instance, the size, number, activity level, type, and diversity of organisms in activated sludge are all key indicators we can monitor. The F-M ratio, or food to microorganism ratio, that a system operates at, has a direct influence on which types of bugs will dominate. Starting with young sludge, which occurs at a high F-M ratio, you'll notice loose flock particles mainly composed of amoebas, flagellates, and some free-swimming ciliates. The organisms here are fast-growing and highly active, which means the system processes waste quickly and often sends it out before it's fully digested. Next, we have what we call ideal sludge, which results from a correct F-M ratio. In this case, you'll find strong, medium-sized flock particles with a diverse mix of organisms. Notably, you'll see large clusters of stalked ciliates and free-swimming ciliates. This balanced community allows the sludge to settle and compact well, leading to a clear supernatant with low BOD and TSS levels. Finally, with old sludge and a low F/M ratio, the flock particles become dark and dense. You'll see organisms like rotifers, stalked ciliates, and sludge worms. These are slower-growing, lower-activity organisms, which indicates that the system is thoroughly digesting the waste over longer MCRT periods. Understanding these microbial communities and their characteristics helps us gauge the overall health and efficiency of our treatment system. Filamentous bacteria can cause some of the most serious operational issues in activated sludge systems. When these bacteria grow excessively, they tend to interfere with the normal formation of flock particles, which are essential for settling. The key reason for this is their shape. These filaments act like fibers in fiberglass insulation, helping to maintain what's called the loft, or the airy structure needed for good settling. But if there's too much filamentous bacteria, they can actually prevent solids from settling out properly, leading to a condition known as bulking of the sludge. Now, when we look at filamentous bulking under a light microscope, we sometimes see these filaments inside the flock particles themselves. This causes the flocks to expand and become less dense, which makes them unable to settle. You might call this an open flock structure. It's a clear sign that filamentous bacteria are disrupting the normal flock formation. In other cases, these filaments extend from one flock to another, creating what's called interflock bridging. This bridging can be particularly problematic because it leads to severe sludge bulking episodes. If nothing is done to control this, it can cause solids to wash out in the secondary clarifiers, which is a big concern for plant operation. Filamentous bacteria are also involved in foaming issues. While foaming is often associated with fats, oils, and grease in the influent, some filamentous bacteria have evolved to be buoyant. They float to the surface and directly contact these fats. When a large amount of grease enters the aeration basin, these bacteria rapidly break it down, and that process often results in foam formation. This foam layer can become a persistent problem, impacting the overall treatment process. So, understanding these behaviors of filamentous bacteria is crucial because they directly affect the efficiency and stability of our activated sludge systems. Managing their growth is key to maintaining proper solids separation and preventing operational disruptions. Let's take a closer look at some common types of filamentous bacteria and how we can identify them under the microscope. Beyond just counting how many filaments, there are noting whether they're in the flock, between flocks, or in foam. Identifying the specific type of filamentous bacteria can really help us understand what's causing a bulking event. When we know which bacteria are involved, it often points directly to the underlying cause of the overgrowth. For example, type 1701 tends to cause bulking by creating an open flock structure, and this is often linked to low dissolved oxygen levels. Spheratillus natans, on the other hand, causes bulking through interflock bridging, especially under conditions of high food to microorganism ratios, or F/M, combined with low dissolved oxygen. Microthrix parvicella is another common culprit, leading to bulking and persistent tan foam. This bacteria thrives in the presence of excess fats, oils, and grease, particularly when F/M is low, and growth can increase during temperature changes. Moving on, types 21N and Thiothrix I and II tend to induce bulking through a combination of open flock structures and interflock bridging, often under septic conditions, low F/M, and nutrient deficiencies. Nocardia causes bulking with a characteristic leathery, dark brown foam, commonly when there's an excess of fats, oils, and grease, especially in colder temperatures. Beggiatoa species also cause bulking with open flock structures and interflock bridging, typically in septic conditions. Lastly, fungi tend to be associated with open flock structures, often due to low pH in the influent or aeration basin, which is common in systems that nitrify. By identifying these types under the microscope, we can get a much clearer picture of what's driving bulking issues and tailor our control strategies accordingly. Let's talk about preventing and controlling bulking, which is essential for maintaining a healthy activated sludge process. As the old saying goes, 1 ounce of prevention is worth a pound of cure, and that really holds true here. First, maintaining the correct F/M ratio is crucial. We need to carefully review our plant records to determine which F/M ratio produces the best quality effluent and stable settling over the long term. It's important to keep an eye on influent solids loadings and regulate sludge wasting rates carefully to keep the solids in the aeration basin at the right level. Next, we should prevent low dissolved oxygen levels. Using a calibrated field DO meter, we can quickly and accurately check the DO concentration in the aeration basin, ideally at least once a week. Generally, maintaining at least 1 mg/L of DO helps keep the process stable and prevents filamentous bulking. Controlling grease entry is also a key step, especially when dealing with problematic filaments like Microthrix parvicella and Nocardia. To do this, we need to prevent grease from entering the sewer system. Using tight mesh screens or fine screens, along with primary clarifiers, can significantly reduce grease loads in the aeration basin. Another effective strategy is employing anoxic zones. These zones create environments where soluble BOD in the influent is rapidly taken up by the desirable bacteria. Many filamentous bacteria struggle to compete in these conditions, so anoxic zones help select against their growth, improving sludge quality. Finally, RAS chlorination should be considered as a last resort. When bulking gets so severe that solids are washing out of the secondary clarifier, chlorinating the return activated sludge can help. Remember, this method should only be used after other control measures have failed. The typical dosing is between 1 and 10 pounds of chlorine per 1,000 pounds of MLVSS per day, spread over a 24-hour period. By carefully managing these controls, we can prevent bulking problems and maintain a healthy, stable activated sludge process. Responding to process changes is a critical part of managing a treatment plant effectively. One of the most valuable tools we have is maintaining a complete and accurate record of the plant's operating history. This helps us understand how the plant behaves under different conditions, especially since most plants experience seasonal variations throughout the year. Once we identify the right response to a particular change, we can apply that same response reliably each year, which improves consistency and performance. Most plants have a certain mixed liquor suspended solids concentration where they perform best, and knowing this helps us optimize operations. Record keeping is essential. By documenting operating history, seasonal fluctuations, and responses that worked, we build a valuable reference for future adjustments. Monitoring changes is also key. We need to keep track of temperature shifts, flow variations, loading patterns, and the impact of seasons on system performance. This data helps us understand what's happening in real time and guides our decisions. Assessing current conditions involves looking at several indicators. The F/M ratio, SVI, microscope analysis, and visual observations all give us a snapshot of how the system is doing right now. It's about understanding the current state before making any adjustments. When it comes to making changes, remember, never alter any process parameter by more than 10% per week, and only change one major factor at a time. This approach helps us determine what's actually working without causing unnecessary disruption. After implementing a change, give the system time to stabilize, usually about a week, but some plants may need up to a month. Patience here ensures that we see the true effect of our adjustments. Finally, it's important to evaluate the results carefully. We review the effluent quality, settling characteristics, and overall system stability to confirm whether our adjustments have been successful. As the plant ages and load increases, operators need to respond accordingly. Over time, most operators become very familiar with their plant's likes and dislikes. Running an activated sludge process successfully really depends on a skilled operator who understands the many control factors and is constantly monitoring and adjusting as needed. That's the essence of maintaining optimal performance over the long term.